dynamic features, current match situation, static features like team strength, winner of toss, and home advantage. Use wall by wall data for 1300 plus.
Do you remember when we did the example from my class with the it was the Bradley Terry model? I don't know if you remember. It
Yes,
had like the
I
base.
think it
I
is.
think that's like
Yes,
this, right?
yes, yes. This is somewhat like that. So best in play of 55%, initial phases, model to team strength more important. So this is basically like my quick take is we have a bunch of features. Example being which team won the toss or team strength and maybe some few others. And we divide a cricket match into various stages, like the early part, middle part, late part, or something like that. And then we want to understand which feature matters, which feature is more important in terms of predicting the match result at each stage.
So it's updating during the match as well too, right? Like there's a
So you
win.
can imagine like from the early part of the match, there is not much has happened in the match already. So the current score may not be very that important. Rather, the team strength or toss, that those things are more important. But when it's like the very end part of the match, then the team strength doesn't matter much because most people have already played or out or whatever. What is the current score, current situation matters more. So something like that they are trying to do. So they're saying this can be useful in preparing some in-play winner, which some apps nowadays do pretty important does for T20 matches. It gives a win probability for both teams
Nice.
at any point. So
What
that's
is the involvement with the shop though? I know that word keeps gonna keep
I no, they just give a number. They don't actually
the
try to explain.
85% or whatever is okay.
Yeah, they just give a number percentage. So cricket has complex set of rules. Creating quantitative model is difficult. And so they are doing once every over kind of thing, keeping the current match status.
Ah, nice. Okay. So those are like the states, then each over is a state then, I
Yeah, at
guess.
the end of each over, you basically take the team score and check what is happening.
Picked again then.
Then mention some related work. Let's just skip this part for now. This is
Yeah.
just naming a lot of people. Machine learning has been used extensively. The match, yeah, the toss thing sometimes matters a lot in cricket. Sometimes it's like becomes irrelevant, and that's a bit difficult to tell which is which.
That means
Like
who bats
sometimes,
first? Who bats
yeah,
first?
who bats first versus who bats second. Like
Do
sometimes you know that some pitches will the behavior will differ abruptly between the beginning and the end part. So teams also know that if I bat first, I have a natural advantage. And sometimes people don't know what is going to happen, so the decision is a bit random.
That's interesting. Yeah.
Uh, okay, now let's move to session two. Brief overview of cricket match, two innings. You know the basics, I guess, already. So uh, you can skip a lesson. So the prediction. So yeah, so each innings is 50 different states because there are 50 overs.
50 overs, 50 overs then, right? Yeah.
And then the predicted winner, the first and second inning is I1 and I2, take two innings and the scores after every over. So the prediction at S0 and I1 is a prediction even before the first ball. So you can have a prediction before the start,
Home
just before the start.
advantage. Yeah,
Yeah.
whatever
So at
the
that point, you only know who is batting first and who is batting second.
yes.
So you can use that information and maybe some team strength kind of thing.
Yeah.
So end of 50 overs in the is not taken because by that time you already know the result. So first batting team will be A, second batting will be B. And so now we are basically making it a classification problem and we are defining the features. So one feature is ball remaining.
Whoa, 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 wait. I didn't
Yeah.
understand that. How did we make this a classification problem? How did
So
this?
classification problem because you are trying to predict which team will win. team batting first will win or team batting second will win.
So you're literally classifying a winner and a loser. That's what you're
Yeah.
classifying.
Yeah. Yeah, right.
Oh, interesting.
And
Okay.
you know the actual match result, so you know which is going to
Oh,
win that.
so in this example, it would not be the half and the half then that you're setting, right? Like even in the right? Because remember we
You
said
can do half and half. Doesn't matter.
okay.
That will be kind of like symmetric. Okay. So like so my response variable here y is the result of the match 0 or 1 depending on the first team or the second team inning.
Yes.
And then we are trying to define a bunch of regressors.
Yes.
So one regressor is how many balls are remaining. And second regressor is how much the lead kind of thing. And how they defined it
Or
is
difference.
interesting. So in the first innings, lead is whatever runs has been scored. In the second innings, so whatever runs has been already scored by the team one, and whatever run is scored by the team two, and then subtract.
Yes.
So that's basically how much run is remaining to be scored, kind of thing.
Yes.
Cricket still requires that plus one thing, like if the first team scored 100, you need to score 101, but we are ignoring that plus one thing for now,
Right. Okay.
just for simplicity. And then there is wickets remaining also usually defined. So if it's 5 wickets down, then 5 wickets are remaining, that kind of
Yeah.
thing. And then there is a relative team strength. This is done on some based on some historical data. You assign a strength to every player, batsman and bowler, and then you calculate it somehow.
Got it.
And then there's a home country advantage they are giving, which they're giving 1+1 to the home team and 0 to the away team,
This is so
and half and half
similar.
for neutral. For neutral.
Yeah.
Okay. And there's a toss also 0 or 1 kind of thing. So these are like categorical variables we are converting to numerical.
Yes.
Okay. So apart from this, every data point has a class level. Class level is 1 when the team B wins and 0 if team A wins. So, and they are citing some people who says that toss matters and team quality matters and home advantage also matters. So these are the three things we basically know at the beginning of the match itself.
Okay. Yes.
And then as the match progresses, we have the score also. So
Yes.
all those balls remaining and wickets remaining and runs remaining, all this.
Wait, so at the start of the match, we only have three regressors.
Yes.
Okay. And then
The
as the
toss,
match goes,
the
we have
team
the six.
quality, and the home advantage.
Yeah. So then as the match goes, we have all six of them then. Is the team strength going to be changing during the match?
No, this is
No, that's going to be
everything before the match. So that is like fixed.
okay. Got it.
Okay. I think better would have been like which batsmen have already played and which batsmen are yet to bat.
Mm.
That kind of thing would have been done. But
I
like
have
they are
to
not
even
going.
mention, I have to mention in the presentation how to make this better. So that can be one that I can mention also.
So
Yeah.
one thing that can be that which batsmen are remaining to be batted. So for
Yeah.
example, if one team has a really great batsman who is basically making that team very strong, but let's say he got out in the first over,
Yeah.
then basically then the team strength should be adjusted accordingly
Yes.
because most of your strength is coming from one player who is already out, so he cannot bat anymore.
Yeah.
That kind of thing. But the problem there is to do that, you need to collect data on which batsman is out and all that. So
Yeah.
you need to get some data.
Yeah.
What they are doing is probably a little bit less data. Okay. So now section 3 is all about how do you give historical value to batsmen and bowlers.
Right.
So first we'll do batsmen and then bowlers. So batsmen have this batting average thing. You probably already know this. How
Yes.
many runs the batsman typically scores before getting out.
Yep.
And batsman also has a batting strike rate, which is like how many runs you have on an average score every 100 balls.
Yeah.
And then their definition is just multiply the two things. That's the batsman score.
Cool.
And bowler also
It's
you can do
pretty
something
simple
similar.
calculation there. That's not very
Like
complex.
bowler also you have an economy rate. which how many runs you give every 6 balls, and you have a strike rate, how many wickets you take every ball.
Cool.
Okay. And then you do 1 over this 1 over because like for bowler, lower numbers are better. If you give less runs, it's better.
Yeah, you want to, yeah, you want a lower number there.
That's why they have defined 1 over.
Oh, but then it'll
It's
flip it so that you have a higher, then it's higher number. Okay.
higher numbers better.
Okay.
And if a player didn't bat or bowl in the 10 data set, we said that goes to 0. So you can have some newcomers who is playing for first time. For them, the strength will be 0.
Got it.
So, and they also note that some people may have played only 1 or 2 matches and did really well in that. So they will have very high scores. So that is basically small sample kind of problem. So they do some capping.
Oh.
And then they have an algorithm to calculate the team strength.
Capping would just be a way to not skew the data for players that don't
Yes,
have much data on them, then, right?
yes, exactly. There are, if you want, there are better ways of capping. So one is very good Bayesian capping, Bayesian update.
Bayesian update. Okay.
So Bayesian update, what it will do is it will look at, let's say, the whole universe of all batsmen,
Okay.
and it will look at for this particular batsman, let's say he has played 5 matches or
Yeah.
n matches, and based on that his score,
Yes.
and it will do a weighted average of these two things
Got it.
in such a way that if you play more matches, then your score will get more weighted. And if you play very little matches, then you will get basically
League.
the league average basically.
Yeah.
So that will automatically adjust. If someone has played no matches, you will get the league average.
Yeah, that makes sense. That
And
makes
if you played a lot of matches, then you will get your own score, basically has more confidence. So the league average will be ignored.
That was called Bayesian update, right? You said?
That's the Bayesian update. So this is like a direct formula. If you assume some normal distribution or something and then do the Bayesian posterior
Got it.
calculation.
Cool.
So Bayesian posterior mean and stuff like that. That's one way we can input this. And then we have a team rating, which is basically you calculate the relative team strength for batting and bowling side, and then do subtraction data.
And
Batting over bowling minus for team B by team A minus batting of team A by bowling of team B.
okay. Calculation of the relative team strength. Okay, so this is what we're doing
So
here.
you take the batting of team B. So when team B is batting, the team A will be bowling. So you take the ratio of those two teams. And then when the team A is batting, then team B is bowling. So you take the ratio of those two teams and then take the subtraction.
Yeah. And this will be the
So that's
strength of team M, right? Yeah. Okay, perfect.
the relative strength of the match.
Relative strength of the match. Relative strength of them. I'm sorry.
So relative strength of B versus A in this match for
Got,
this A-B pair.
okay, got it.
Okay. And that is basically our regression.
Got it.
Okay. One advantage of doing it this way is uh, something we have ignored talking about is the batting score and bowling score doesn't have same units.
Oh,
So, for example, batting score might be batting strike rate might be let's say 120 and batting average might be 30. So 120 times 30, which is a large number. And for bowler, it will be 1 over some numbers, it will be a very small number. So
yeah.
if you try to directly sum or subtract or something, it doesn't make much sense. Bowlers will be neglected.
Yeah.
By taking a ratio of this way, so both A team bowlers and B team bowlers go into the denominator. So they will be treated equal.
Got it.
So that's like one smart way of doing this.
Mhm.
So let's move on a bit. Data set. So we have data set which was they are taking quick set. Good. And then the ball body all data is available in the JSON format. So they have converted this to Python stuff. They'll probably have some code somewhere. So we are considering only men's ODIs. So non-international matches are ignored and women's teams are ignored. and only matches played between the 10 full members. So there are smaller teams, they are also ignored
Hmm.
because they'll have very few matches. And also matches which has rain and stuff is very complicated because the cricket has a duckworth kind of rule. I
Oh,
don't know if you've heard of.
right.
So that has some complications of its own. So they're ignoring those.
It would
And
be cool
tied matches.
to, I guess, it would be, could you have a regressor for weather then? Is that a condition? I don't, that would be too hard to model.
No, because whether you don't know beforehand.
Yeah, that's true. Yeah. Yeah.
So it's difficult to predict whether the match will get over or
Or
there will
change.
be a rain in. Yeah,
Yeah.
so that will be difficult. By the way, Duckworth is a statistical thing that you know that
Say again?
the Duckworth method that cricket uses if there is rain and you have to play, say, instead of 20 overs, you will play 10 overs, how much you will score. So there are some adjustment rules and all that.
Oh, cool.
That's very much like basic statistics, exponential distribution and stuff.
Basic statistics for you or basic statistics for me?
Like you have covered most of the maths in that.
Oh,
You know exponential distribution,
yeah,
the lambda
that's cool.
parameter and
I
all that.
didn't.
Yeah. So it's based on that. And those both of those people are statistical.
But can you say it again?
Duckworth and Lewis. You have the name here. You just Google the name and you'll find the
Oh,
method.
Duckworth and Lewis. I didn't see that. Duckworth and Lewis method. That's so cool. Oh, DLS method to set a
Yes.
fair adjusted target for the team batting ends and the match is interrupted. Oh, very cool. I'll have to look into that. Oh, there's a they have a Duckworth Lewis
Yeah,
calculator.
yeah, they're online calculators.
Nice. Cool.
Yeah. So next, they're doing some data preparation. Okay. So they're doing 25% for testing and rest will be training data.
Okay. Is
So they're
1359, is that enough matches, do you think? Is that a lot of matches or 1000?
should be fine, I think. I think
That
should be
should be
fine.
fun.
But because every match you also have every over. So you have
That's true.
100 overs in a
Yeah,
match,
you
so
have,
100
yeah,
points.
that's
So
true.
this times 100 basically.
Yeah, that's true. You have 100 overs.
So then basically you have a lot. But the thing is, within a match, let's say you have 100 data points, all of them will have the same response.
Yeah,
So that's one limited thing.
that's true.
But I think, yeah, 1359 is fine. It's not small. So now nature of the data is different in the first and second innings. So for example, when the first innings is going on, you don't have the second innings score, but second innings you always have a target in mind. So that's why like you have to kind of separate the first and second innings prediction to work differently.
Why?
And
The teams are switching. That's what you mean?
no, no, not because of that. So when the first team is batting, so you have only the first team score. Let's say they have played 20 overs, they have a score after 20 overs, say let's say they scored 100 something runs. But
Yeah.
when the second team is batting, let's say in 20 overs they scored 100 runs, but you also know the first team score. So you have a target and you compare relative to that target of 300 something, they have scored only 100 runs so you can compare. So you
Yeah,
kind of have more data in the second inning in a different way.
that's true. Gotcha.
So you have to compare relative to the first innings batting, whether the second innings is falling behind or not. That kind of idea.
Yep.
For first innings, you cannot do that kind of
You don't have
comparison.
a reference point then.
Yeah, you don't have a reference. Yeah.
Okay.
So, and then, so yeah, as we discussed, we have three things known at the beginning, the relative team strength, home country, and toss. So these we need to calculate at the beginning of the match. And then the other things like balls remaining, wickets remaining, lead, these things change throughout the match.
Yeah.
Okay. And the lead thing actually like starts at zero. At the beginning, you don't have any run score,
Yeah.
and it will keep increasing throughout the first inning, and it will keep decreasing throughout the second inning.
Yes.
So you have a nice pattern there. And the player valuation are computed using the data from the second inning. The training set only. So try to avoid. Yeah, understand. So the point they're mentioning is that you cannot use the training test data to like calculate anything about the training data. They have to be separate.
Right.
So
That's
when you
pretty,
calculate the player strength, you have to use only the training data part to calculate the player strength.
yeah. That's pretty common though, right? You don't intermingle those, right?
Yes. Yeah, that's pretty standard. And if you have an unknown player, we determine the playing role, whether it's the batsman or bowler or all-rounder with the cricket board side. So they mention whether a player is a batsman or a bowler or
Hmm.
all-rounder. That kind of stuff. And accordingly, they have some average values performance given for a batsman, bowler, and all-rounder.
Well, for an unknown,
Yes.
I don't know, they just do a league
So this is
average,
basically the default value when you don't have data.
the default value. Yeah.
Okay. And they're saying we don't have same number of training points for all the states. Yes. So there is a bit of problem there, but I think that should be fine. I don't see that as a real concern. So most cricket matches will like basically end because the second team like scores the first team crosses the first team's runs before the 50 overs.
Right.
So like whatever the first team scored, they able to score in 40 something overs, let's say.
Right.
So then you don't have data for the remaining say 49, 50 those
Yeah.
overs.
Yep.
So you have a little bit less data in the second innings
That's
sometimes.
true. That's true. Does that affect the model at all though?
Not much because most times your data will be about at least 40 overs. The
Overs.
second team takes mostly about 40 overs or more, even if they are successfully chasing.
Yeah.
But for the last few overs, like 49 or 50, mostly you will have data when the team is not being able to chase.
Okay.
If they're able to chase, they will probably most likely finish before that.
Got it. Okay.
So your model might be slightly biased there.
Got it.
So you will mostly have data when the second team is bad.
When the second,
But we, yes,
because you'll have the
so
full
but
50 overs out
yes,
of them. And yeah.
yes. But like you also have the team strength. So hopefully that will take care of that a little bit.
Yeah.
So from the team strength, we will already know that the team is bad. So that will remove the bias to some extent.
If,
And
hey, quick question, this is a cricket question. In the match, let's say team A bats first, they score
yes,
400 runs, and
yes,
then team B is coming up to bat, but they're in the 49th inning, 49th over,
over, yes,
um, but they're down by 200 runs or something.
yes.
Will they still play all 50 overs then still, even
Yeah,
if
yeah, you have to play.
you have to, even
In
if
one
it's
day, there is no
mathematically
force
not,
fitting. Yeah, you have to play.
you have to play. Okay, got it.
Sometimes there are other reasons for playing, like it's a tournament, you still get some points for how much
Oh,
runs you have scored.
6
And
or
that might matter in the later stage or something like that.
got it. Okay.
Okay. So like if two teams have each one same number of matches in the tournament, and you want to decide who goes to the semi-final or something,
Yeah,
then you use those data. So that's like a
makes
tiebreaker kind of thing.
that makes
So
sense.
for that reason, people choose that. Okay. So let's see now they are trying to do data analysis. So training data has this many matches where team B lost and this many matches where team B won. So that means this many training data points for level 0 and level 1. And this many class level 0 and level 1. Second, basically, this is the size of the data. 18,000 and 17,000 in the first inning of both timed responses
Yeah,
and 16,000 and 15,000. So you can see it's a bit lower. The second innings is 16,900 and 15,000 in the second of the phase. So, and this is the relative team strength. Uh, what have they plotted? So, the result of team B is in the horizontal axis and the team strength. So, depending on how far the team is, you can see that the team is changing a little bit. This is a box plot of that.
I don't understand this box plot. It's what is the 0 and team
So
B1?
the horizontal axis is 0 and 1, meaning the right plot, the orange one is when the second team won, and the blue one is when the first team won.
Okay.
Okay.
Yeah.
And then the vertical axis is the relative strength of the team, meaning if you go higher, that would mean that the second team is better.
Okay. Okay. Got
Okay.
it.
So you can see that the orange thing is naturally a bit higher because if the second team is better, they have more chance of winning.
Yeah, that makes
And the
sense.
blue thing is a bit lower because they have less chance of winning.
That makes sense.
If you look, will pay a little bit more attention. So you see the 0 on the vertical axis, right?
Yes.
And there's a horizontal line from the zero,
Yes. One is above.
and yeah, one is above and one is below, and roughly equally above and equally below.
Yes. That makes sense.
And then there is this. So they are basically doing some exploratory data analysis by doing a bunch of plots. So this is home country versus away country advantage. How many matches the home country has won, the away country has won, and neutral matches.
What is 0.5 then?
So the neutral matches, they are doing 0.5 to each. Like each team is half home and
Oh, a
half away.
neutral match, meaning they're not on either of
Just to, yeah,
those.
just to convert to a number. Okay. And then this is the toss result, like winning toss versus losing toss.
Got
So you
it.
can see in both cases, team winning toss wins more matches.
Oh, interesting. That's a little bit significant there. So today, that's
Yes, there is some significance, definitely.
yeah, that's interesting.
Yes. And also like it has a little bit of confounding effect of the variables, because if the second team won the toss and won the match, that means they were expecting that batting second is better thing to do.
Right.
Versus if the team first team is batting first and won the match, that means they were expecting the first batting first is the better thing to do,
Yeah.
right? So this is to an extent like how much convinced they are about, and how much information they have about whether batting first is better or batting second is better.
Yeah. Yeah. That's
Like quite often teams get that wrong. They choose to bat first, but bat first was like after a few overs, people will realize bat first was a wrong decision. But
yeah.
they cannot change at that point. So they're stuck. So all those things comes into picture. Okay, and then this is the balls remaining thing. This I think has less effect.
Oh, interesting. Yeah, this has less effect.
Yeah, this seems to be like very close to each other.
So I guess they're taking each of these regressors, showing the
And
improvement
showing how the plot looks like.
through the box and whisker plots then, right?
Yes. And this is the lead thing that we discussed for first innings and second innings.
Lead. Yeah. So this
For
is
first
during
innings,
the game then. These are all of the ones during the
these are
game.
during in-game data.
Dynamic. Oh, the dynamic features they call it. Yeah,
Yes,
exactly.
the dynamic features. This is for second
Balls
innings. They have done balls
remaining, the
remaining.
lead of team A, second innings, and then the
And
wicket.
yeah, this is the interesting thing. This is the heat map
This is the
for lessons between the features.
correlations. Yes. Oh wow. Okay.
So, for example, you can see that the balls remaining and the wickets remaining has a 0.75 correlation, which is expected because as you are losing more wickets, as you are like going to progressing in the match, you are losing both balls and wickets.
Yeah.
Other than that, like there are some negative values, like balls remaining with the lead of team A, that is like very close to -1,
Yeah.
which also makes sense.
Yeah.
So this is basically all the explanatory thing, and this is again the same thing for second innings. So because we discussed like the first innings and second innings prediction is a bit different, there are some of these things you have to do separately for first and second innings.
Oh, okay.
So you have to be careful and protect that. Like they work, the mindset thinking also work quite differently. Second innings you have a set target, so you try to reach there. First innings you don't know what
As
is the
much as
target, so you do as
possible.
much as
Just
possible,
keep
as
going.
much as possible.
Yeah.
Yes,
That's true. The strategy is different then, right? Yeah.
strategy is a bit different. And this is again the heat map. So here the correlation numbers are that's why a bit different. The lead and the ball remaining position is highly positive. This is negative on the previous one. Okay. And then they are basically throwing in a bunch of classification methods. I think whatever they got. So let's see. They have knife base, decision tree, random forest, logistic, k nearest neighbor, and neural network.
All of those can be used for classification.
Yes, all of them can be used for classification. Other than the last one, others are quite straightforward.
The neural networks, yeah, yeah, yeah. We did
Yeah, that's
logistic regression. Logistic regression is there. Nice.
we haven't discussed decision tree or random forest, but they are basically easy.
Yeah, I think the next one that's coming up actually is K nearest neighbors, and then we do the trees in the
The
forest
tree.
after that.
Okay.
So what
So
they're modeling the accuracy of each of these models based on number of correct predictions over the total number. Which one is, oh, neural networks is the, oh no, logistic regression is the best?
yeah, logistic is best. Almost, I think. I don't know. These two looks almost equal, logistic and neural network. By the way, logistic surprisingly works like extremely well in lot of practical situations,
For classifying.
even in yeah for classification.
Cool.
A lot of banks use this, for example, for retail banking. You want to know whether something is a fraud or not. Some
Right.
transaction has a fraud detection kind of thing. So they use logistics. So that's like the industry standard
Nice.
and it works well. And there are a lot of other such applications where logistics works well. So,
For this
and this,
logistic regression, though, because we said, right, it'll be binomial, right? It's just
yes,
win or
yeah,
loser
it is binomial. There is a two-way classification, so
in my classification.
it's not multi-way. And for second inning, you can see the random forest does well, almost same as on the neural network. So neural network is like far more advanced compared to all the other. I would expect it to do a lot better, but if the others are doing almost equally well, that means they're doing well. Or neural network is not basically adding much value there.
That's interesting.
But in terms of being able to explain what is happening, all the others have some intuitive explanation, neural network doesn't.
Yeah, got it. It's just a
So
black box more like, is that what you're
yes,
saying?
more like a black box. It works very close to a black box. So that's the case. And
Can you give me a 10-second description of the random forest?
okay. Do you know decision tree?
I can visualize it. I don't know how it's gonna like if it follows along a path, then it falls under a certain classification. Is that maybe
Yes. So basically you do, okay, if my first regressor is less than 50, then you make a tree structure. And at each point you have a node, you have a question. Whether first regression is less than 50, you go left. If it's greater than 50, go right. Then
okay?
second regression is less than 50, less than something, you go left, otherwise go right. And you create a whole tree here, and then every leaf node will tell you whether what my prediction is.
Yeah. Okay.
Okay, so that's decision tree. And this tree can have different levels of depth, which means how many questions you ask, and different number of regressors you can use, and all that, right?
Yes.
Now, if you do that for any training data set, there is a chance of overfitting, meaning
Yes.
your data might have had the case that there was no combination of x1 being small and x2 being large. So that's why all those gets confounded and being classified in a certain way.
Right.
So that's why if you allow decision trees to be high depth, they usually do very much overfitting. And in sample, like training sample, they do well. Trace sample, they do horrible.
Okay.
Okay. So that's why decision trees people try to like restrict the depth,
Got it.
but that also restrict the performance. So the solution there people use is you do randomization, meaning I will do the decision tree. I will only allow up to certain depth, but I will not use all the regressors. Let's say I have 20 regressors. I will allow, let's say, three of them and create a decision tree.
Okay.
Similarly, I can use some other set of regressors. I create another decision tree.
Got it.
Okay.
Interesting.
And let's say I create 20 different decision trees like this.
Okay.
Okay.
Well,
And then I do a voting between them, who like what is their predictions and try to combine.
so are you picking one tree out of all of that, or that's the best,
No,
or are
no,
you're
no.
using?
I am asking all the trees to say what is your prediction.
So why would you ever use a decision tree as opposed to isn't random forest automatically going to be better every time?
At the cost of
No
much
cost.
more complex to explain.
Yeah.
Not just cost in terms of computation, but cost to explain also what is going on.
Cost and
Essentially, I can to explain what is happened, like how the decision was taken.
okay,
When
explain.
you are predicting something in real world, people want to ask you like, how did you come to that? How
Yeah,
did you arrive at the decision?
yeah.
So that is difficult to do for random forest.
Okay, got it. So many
Okay.
trade-offs with
So
those.
that's the cost you pay of getting a complicated model versus a simple model.
Got it.
So that's how basically the random forest part works. And there are other techniques to improve it. Bagging, boosting, these are basically different terms.
Anything.
Yeah,
I've
yeah.
heard all
People
these
try and
words. I've heard all of these words, Sajay. It's nice to like put them together and know what is what now. It's just
like,
going to be the actual methodology that I need to learn on each of these methods. So,
yeah, yeah. I just need to spend a little bit of time.
oh,
It's not
also,
none of this is very difficult.
yeah. And none of them is hard, difficult to conceptually understand, right? I think it's actually like creating the model and
Yeah.
actually training a model. So,
And in practice, you will mostly use some Python library or something to
but yeah,
implement
that's
this. So
yeah,
you are not going to do any of this by hand, except linear regression you can do by hand.
yeah,
Nearest neighbor also you can do by hand, but others you would never do by hand.
nice. Okay, buddy, should we pause here today? Sorry, man, we
Yeah,
went over
let's do that.
time. So, yeah,
We'll catch it again. Next week you're available?
yes, please. Yeah, next week I have no school on Thursday, Friday, Saturday, Sunday. So no
Okay,
classes. So
fine.
I'm just gonna be, I need to start prepping for my midterm exams. So I'll be
Okay,
studying all weekend. So yes.
okay, good.
Okay. Thanks, buddy. Oh, dad is out of town, so Jay. So
Okay,
is
okay.
it, he said, is it okay if he comes back? He'll be back, I think,
Yeah, that's good.
next week, and then he'll send the money for January
Yeah,
though.
that
So
should be fine.
okay, sounds good.
Okay, thank you.
Thank you. Bye bye.